You know, for the longest time, chemistry had this huge blind spot. We had theories that could explain how atoms bonded, why reactions happened, but they couldn't really explain something as basic as color. Why are some chemicals just bursting with color while others aren't? Well, it turns out a surprisingly simple idea was all it took to crack the code. Let's dive into it. It's called Crysta Field Theory, and it's the beautiful model that finally connected the invisible world of electrons to the vibrant colors we see every single day. So let's start with a classic mystery. Why is something like copper sulfate, a pretty common chemical you'd find in a lab, that brilliant blue? And at the same time, why is a ruby, which is really just aluminum oxide with a tiny bit of chromium mixed in, glowing with that incredible deep red? The answer to both is all about how a central metal atom interacts with its closest neighbors. And that's exactly what we're going to unpack today. So, here's our game plan. We're going to start with this mystery of chemical color. Then we'll meet the key players, the metal and its partners. After that, we'll get to the main event, orbital splitting. We'll see how electrons have to make this crucial choice between high spin and low spin. And finally, we'll put it all together to solve for color and magnetism, and even take a quick peek at how this theory works for different shapes. Right, so that amazing range of colors you see in compounds made with transition metals, that's not random. It's not just for show. Think of every single color as a direct visual clue, a breadcrumb trail that leads us straight to what the electrons are doing, deep inside the atomic structure. Now, to really get this, we need to meet the two main characters in our story. At the very center of it all, you've got a transition metal ion. But here's the thing, it's never alone. It's always surrounded by a group of other ions or molecules that are bonded to it. And these partners, they're called ligands. So what exactly is a ligand? Well, the easiest way to think about it is as a Lewis base. It's got at least one pair of electrons that it's ready and willing to donate to form a bond. The central metal, in this case, acts as the Lewis acid. It's the electron pair acceptor. This whole interaction, this donation and acceptance, is the absolute foundation for everything we're about to talk about. And we even classify ligands based on how they attach to the metal, using this really cool analogy that comes from the Latin word for tooth. A monodentate ligand, like a water molecule, takes one bite at the metal, connecting at just a single point. But then you have polydentate ligands, and these guys can grab on with multiple teeth. Ethylene diamine, for example, is bidentate. It bites down in two spots at once, wrapping around the metal and forming this incredibly stable structure. Okay, now we're getting to the absolute heart of the theory. This is where the magic really happens. When those ligands get close to the central metal ion, it's not just a simple bond that forms. Their approach triggers something dramatic. It's an event that completely changes the energy landscape for the metal's electrons. So before any ligands show up, things are actually pretty boring. If you have a metal ion just floating in space all by itself, its 5d orbitals, even though they have different shapes and point in different directions, are all at the exact same energy level. In chemistry, we call this degenerate. Just picture a perfectly level playing field, where every spot is just as good as the next for an electron. But that level playing field is about to get completely torn up. Let's imagine 6 ligands marching in, taking up positions along the positive and negative ends of the x, y, and z axes. Now, the metal's d orbitals that point directly at these incoming ligands, the ones we call the EG set, they feel a massive electrostatic repulsion. Bam! Their energy shoots way, way up. But the other orbitals, the T2G set, are kind of tucked in between the axes. They're less affected, and their energy actually drops a little. And just like that, the degeneracy is broken. The d orbitals have split into 2 different energy levels. All right, so the orbitals have split. Now what? Well, this creates a fascinating new puzzle. As we start adding electrons into these orbitals, they're faced with a really important choice. And this choice creates 2 totally different possible outcomes for the complex. It all comes down to the energies involved. I want you to put yourself in the shoes of an electron. Imagine the first 3 electrons have already taken their spots, one in each of the lower energy T2G orbitals. Now, you show up. You're the 4th one. What do? Do you pay the energy price to squeeze into a room that's already occupied and pair up? Or do you pay the energy price to make the big jump up to one of those empty but much higher energy EG orbitals? And that choice comes down to a battle between 2 different energy costs, the splitting energy, which we call delta, and the pairing energy, we'll call that P. Pairing energy is just the natural repulsion electrons feel for each other. It costs energy to shove 2 negative charges into the same tiny space. So if you have weak field ligands, that energy gap, delta, is really small. It's actually easier for the electron to make the jump than to pay the pairing cost. This gives us a high spin complex with as many unpaired electrons as possible. But with strong field ligands, that delta gap is huge. It's way easier to just pay the pairing energy and stay downstairs. That gives us a low spin complex. So you see, the ligand strength decides everything. So how do we know which ligands are weak and which are strong? Well, lucky for us, chemists have already done the hard work and ranked them all in what's called the Spectrochemical series. It's basically a cheat sheet. On the weak end, you've got things like chloride, which cause a tiny split and lead to high-spin complexes. And way over on the strong end, you've got cyanide, which causes this massive energy split and almost always gives you low-spin complexes. It's an essential tool for predicting how these electrons are going to behave. And now it's time for the big payoff. We've just built this entire theoretical model of splitting orbitals and electron spins. So how does any of this connect back to the real-world stuff we can actually see and measure, like the colors and the magnetism we talked about at the very beginning? The origin of color is tied directly to that energy gap, delta. It's amazing. When white light, which contains all the colors, shines on one of these complexes, a photon with the exact right amount of energy, an amount equal to delta, gets absorbed. That energy is used to kick an electron from a lower 2G orbital up to a higher EG orbital. So if the complex absorbs photons of orange light, that orange color gets removed from the spectrum. Your eye then sees all the other colors that pass through, and they combine to look like the complementary color, in this case, blue. That blue of copper sulfate, it's literally the color of light that wasn't absorbed. In magnetism, that connects right back to our high spin versus low spin configurations. High spin complexes, with all those lonely unpaired electrons, are paramagnetic. Each one of those electrons acts like a tiny magnet, so the whole compound is attracted to a magnetic field. But low spin complexes, where all the electrons are neatly paired up, are diamagnetic. They're actually weakly repelled by a magnetic field. This is something we can physically measure in a lab to confirm our predictions. Now, of course, the chemical world isn't made up of only perfect octahedrons. And what's so powerful about crystal field theory is that it's not a one-trick pony. It's incredibly versatile and can adapt to explain the properties of complexes with all kinds of different shapes, just by thinking about where the ligands are. Take a tetrahedral complex, for instance, with 4 ligands. Here, the geometry is totally different. The ligands sneak in between the axes instead of right along them. And the result? The entire splitting pattern gets flipped upside down. The orbitals that were low energy before are now high energy, and vice versa. Plus, because they don't have that direct head-on interaction, the overall energy split is much, much smaller. In fact, get this, the splitting energy in a tetrahedral field is only about 44% of the splitting you'd get in an octahedral field with the very same ligands. That tiny energy gap means tetrahedral complexes are almost always high spin. It's just not worth the energy cost for the electrons to pair up. And then you get weird ones, like square planar complexes. Here, you have 4 ligands all arranged in a flat square on the XY plane. This causes a huge amount of repulsion for any orbitals that have parts lying in that plane, which sends their energy just skyrocketing. This creates a really large and pretty complex splitting pattern that almost always results in a low-spin complex. So when you step back and look at it, crystal field theory is this beautifully simple model. It just treats ligands as points of negative charge, and yet it gives us this incredible power to predict and explain the color and magnetic properties of so many compounds. Which leaves us with one final really fascinating question. If we understand the rules of the game this well, can we move beyond just explaining and start actively designing? Can chemists now pick just the right metal and just the right ligands to engineer new materials with exactly the colors and properties they want?